Hi, and welcome to this SUSECon 2025 talk regarding SUSE Virtualization and its connection with NetApp storage. My name is Daniel Druck. I'm a senior DevOps engineer at FullStacks. We are a SUSE partner. I'm also a community organizer and the founder of Cloud Native Austria. If you want to get in contact with me, reach out via my website or drop me an email at daniel.druck@fullstacks.eu. Now, the agenda for today first copes with a little introduction to SUSE Virtualization, formerly known as Harvester in a nutshell. Then we're going to talk about the storage layers in Harvester, namely the node, virtual machine, and Kubernetes storage. I'm going to give you some lessons learned from our Harvester projects and a little outlook about the close and not so close future. Now, let's start with what SUSE Virtualization, aka Harvester, actually is. Well, in a nutshell, this is what the architectural diagram, very high level, of SUSE Virtualization looks like. SUSE Virtualization actually is an HCI solution, which means a hyper-converged infrastructure. This kind of system provides compute, networking, and storage capabilities in one solution. Now, from a product point of view, SUSE Virtualization is actually a software product, so you need to bring your own machines, your own hardware, which we can see here labeled as node, and then you install SUSE Virtualization, for example, via an ISO file onto that node. SUSE Virtualization actually consists of a Linux, which will then immediately install a Kubernetes cluster, an RKE2 cluster, which will then host KubeVirt and Longhorn for compute and storage, which enables you to create and manage virtual machines on top of that, which of themselves, for example, could host another Kubernetes cluster. As stated here, there is support, for example, for VLANs and also for other, for example, external storage providers. We're going to see about the other capabilities in a second. For this slide, it's only important to remember that SUSE Harvester or SUSE Virtualization is a software product that installs a Linux, a Kubernetes cluster, storage, and VM capabilities on top of that, and is an HCI solution. Product-wise speaking, we're actually talking about SLI Micro, so SUSE Linux Enterprise Micro, as the installed operating system, which also contains a software piece called Elemental Toolkit, which is responsible for the capabilities of SLI Micro regarding providing updates, for example, for an immutable Linux distribution. If you're somewhat into edge computing and if you want to know the latest functionalities provided by SUSE regarding operating system management, definitely have a look at the Elemental project, and underneath that also the Elemental Toolkit, which is a very cool and sophisticated but not that easy to learn piece of software, but very powerful. Now, on top of that, we have RKE2 as a Kubernetes distribution used for SUSE Virtualization, since pretty much under the hood, SUSE Virtualization is a Kubernetes cluster with additional capabilities to provide and host virtual machines, storage, and networking capabilities. But SLI Micro and RKE2 is under the hood, the driving engine. On top of that, we have KubeVirt as a project that enables Harvester to manage, create, and operate virtual machines in Kubernetes pods. Besides that, we have Longhorn, which is the default tool for providing storage in Harvester. And we have some additional monitoring and observability capabilities provided out of the box on top of that as well, namely a stack consisting of Prometheus and Grafana for basic observability of the virtual machines and the pods in this cluster. So this is what SUSE Virtualization looks like from a very high 10,000 foot point of view. If you think about the storage layers in such a system, there are namely three. We have the storage layer on the very bottom, which is the node storage, which is actually the storage that's being used to install SUSE Virtualization or Harvester. so to install the Linux on, pretty much. The next is the VM storage. So this is storage that can be consumed by the virtual machines created in SUSE Virtualization. And the last piece of storage, drawn here on the very top, but this is also true for the Kubernetes within Harvester, is Kubernetes storage, which pretty much will provide storage to pods. All right. Now, since this talk is not only about Harvester or SUSE Virtualization, but this is also about NetApp and how to integrate and combine these systems together, let's have a short look at what NetApp actually is. Well, NetApp is a company that provides enterprise-grade storage solutions. NetApp is very, very renowned for their bulletproof storage appliances. They provide hardware and also software. So they not only ship the disks and the hardware, but they also provide some kind of storage operating system, Linux-based, of course, for their on-premise installations. They also provide cloud storage solutions for your typical public cloud providers. Gonna speak about that in a second, so bear with me. And the thing that you as an administrator most likely will have contact with is either called ONTAP or SolidFire, whereas ONTAP is the storage operating system I mentioned before, and SolidFire is a whole different product, hardware and software-wise, integrated into one appliance, which is specifically focused on high throughput block storage. ONTAP is an operating system that is used with multiple different hardware systems and appliances provided by NetApp, and provides a broader spectrum of capabilities, storage and administration-wise. Now, of course, we're talking about on-premises installations. And if we talk about NetApp on-premise and Kubernetes installations, we also need to talk about Trident, which under the hood is the CSI driver that will do the heavy lifting regarding management, provisioning, etc. Of volumes and storage on NetApp for a Kubernetes cluster. So we're talking about NetApp, appliances, ONTAP and SolidFire, on-premise installations managed by a CSI driver called Trident, which is provided by NetApp, of course. Schematically, this looks something like this. We have the compute layer with Kubernetes and NetApp and Trident as the CSI driver. And on the other side, we have the storage layer, which could pretty much be anything. Since Trident is very versatile, we could, for example, make use of ONTAP and on-premise appliances, which is the typical case you might see, especially in on-prem environments. There is also the possibility for cloud volumes run on ONTAP. And there are also these cloud provider storages that I mentioned before, for example, on AWS, Azure, or Google Cloud. That can all be used for this case. Now, let's have a look at which possibilities we have to cope with the topic of node storage in Harvester. The first option we have is if we have your typical servers with local disks greater than 500 gigs, which is the product environment recommendation. Multiple disks, your typical legacy setup, if you will. The typical solution here is to just go out of the box with Longhorn, since this makes use of local disks out of the box, which is the perfectly fine, reasonable default way to go. But you might run into some kind of performance, lack of performance compared with the NetApp native solution. Since Harvester 1.4, we have the possibility to also use diskless servers, which might look something like this. Cisco UCI blades, for example, connected to some kind of NetApp storage grid, which will then connect via the UEFI to an iSCSI target, which will enable us to boot into this disk, or to make it available to the Harvester installer to install to this iSCSI target. And to do that, we basically have to follow 4 steps, which are all documented perfectly fine, so you don't have to remember that at this point. The first thing you need to do is you need to add the iSCSI target in your UEFI. So boot into the UEFI, hit the delete button as fast as you can. Specify the target name, the IP address, the port. Then you will typically boot from an USB stick or from Pixie Boot or whatever into the Harvester installer. And in the installation disk dialog, you should see a pop-up that references to the first multi-part device of this iSCSI target, which you will then be able to use as an installation target for Harvester. Once you do that, Harvester is configured properly, which is great, but you also need to specify one more parameter in the configuration. Again, this is all documented, so rest assured you can also read about that. But you need to specify these Linux boot options at the end of the day to also being actually able to boot into the root volume once the kernel starts. So what you're going to do here, you're going to specify this drug kernel boot parameters that pretty much tell the kernel to enable the iSCSI boot firmware and to specify that the iSCSI target where you want to boot from, or which you want to mount as the root disk. You need to enable multipath D, and provide some basic configuration. And you also need to take care of the default IP route to set it to the proper interface for startup. And that's pretty much all you need to do. Then you're able to install from diskless servers onto a volume provided by, for example, NetApp, made available via iSCSI. The second thing, and that's actually where it gets very, very interesting, is the topic of virtual machine storage. Because usually you can still install Harvester on local disk, which is perfectly fine. But if it comes to the bigger load of actually data-wise speaking, the bigger load or chunk of VM data, which is usually way bigger than the few images Harvester needs, you might to look for some external storage grid. Now, the default solution here is to use Longhorn with local disk, as I mentioned in the beginning as well. So the setup looks something like this. You have your multiple servers, you have your local disks, you have your RK2 with Longhorn installed on top. And if you create a virtual machine that needs storage, that needs the disks, Longhorn will create this storage space, usually replicated by a factor of 3. So you're pretty much having the same replicated piece of storage on 2 or 3 nodes on their local disks, being made available to the virtual machine via Longhorn, via RVOs or read-write ones or read-write many, which is a perfectly fine solution. But again, you might run into performance drawbacks. Let's put it that way, especially if you're having lots of virtual machines and lots of storage. Now, the alternative is to use Trident as a CSI driver installed on the RK2 of Harvester, which is of course installed in some kind of server. At this point in time, it doesn't matter if it's installed on the legacy server with local disks, or the approach we've seen before with the diskless servers, since we're installing Trident into the RK2 cluster. Of course, we then have a NetApp system standing somewhere that, of course, needs to be connected physically to the hardware. That's definitely true for both approaches. And in that case, if the virtual machine requests a disk, you need to specify the storage class. I'm going to talk about that in a second, so no worries. And Trident will actually talk to the management interface of NetApp, provide a storage volume according to the required size and quality requirements. And this will be made available via the data interface of the NetApp, physically via the hardware, of course, and then be made available to the virtual machine. So just to keep in mind, the initiator in that case is actually the SUSE Linux Enterprise Micro, the SLI Micro, on the physical server. So the IP address of the physical server. All right. Now, how would you configure Trident? There's one thing we need to talk about before we're actually going to configure that. And this is one downside that this implementation actually still has. And that is that a virtual machine might usually have one too many disks, at least one root or system disk where the operating system is coming from, and multiple data disks. Now, you can use external storage for data disks, but you cannot use it for root disk. So whichever way you go, you will always need, as of now, as of the date of this recording, you will always need Longhorn for the system disks, for the root disks. The documentation says that this allows you to leverage external storage for the virtual machine's non-system data disks. This is true as of now, as of Harvester version 1.4.2. There is a feature being anticipated with version 1.5.0, which should come out quite soon, that will provide third-party storage support for the boot disk and the root disk. So I hope that this is something that will be fixed quite shortly. But as of now, you're only able to use external storage for data disks for virtual machines, so not for the boot disk. Okay, so how would you do that? Now, Harvester comes up with some prerequisites, some requirements, if you will, that a storage system and the according CSI driver need to fulfill. So some of them are, for example, storage expansion, if I want to increase the storage of the data disk on my virtual machine, which is perfectly reasonable. Snapshots, of course, if I want to take a backup or to restore. Cloning might also be the case if you want to create a clone of one VM to a second one. The storage also needs to be able to clonable on the backend. It needs to support block devices, of course. And there is also a necessary support for read-write many operations, especially for live migration. So if you want to switch a virtual machine from one node to the other, both of them should be able to read and write on their storage volumes. Luckily for us, the capabilities of Trident support expansion, support snapshot and cloning, support block device, and they support read, write, and many. The thing I need to mention here is that Trident, as I mentioned before, is able to cope with many different backends, NetApp appliances and storage backends, if you will. Depending on which backend you use, there might not be support, inherently not be support for read, write, many operations, but the vast majority of the NetApp storage backends are capable of do so. And the problem here does not lie with NetApp, but either rather with the protocols underneath that just won't support multiple machines writing to the same blocks. All right, now let's have a look at how to install the CSI driver called NetApp Astra Trident. Now, the first thing is, of course, we need to install it in a broader sense, which is actually quite straightforward. This is a Helm chart. It's publicly available. So just install it with your tool of choice. Helm CLI, Terraform, Argo CD, whatever pleases you. The second thing is we need to actually configure the backend. So we need to tell Trident which NetApp actually to make use of, what the credentials are, which IP addresses to use, etc. This is done by Kubernetes manifests. Then we need to configure multipath and IP routes on the nodes underneath. As I mentioned before, in that case, we're actually talking about the Harvester Linux nodes, so the hardware nodes. And the cool thing here is, that, as I mentioned before, SLI Micro is an immutable Linux distribution, which means if you change something, reboot the system, the changes will be gone. The cool thing here is, though, that Harvester comes out of the box with some kind of cloud init custom resource definition, which will actually allow you to create cloud init scripts as a Kubernetes object, and Harvester will deploy them on the nodes. And once the node restarts, these cloud init scripts are being executed or being run. And therefore, you could, for example, just create a cloud init script that will install and configure the multipath package, configure IP routes, etc. So you're perfectly fine to do that in a very elegant way. And again, since this is a cloud init custom resource definition, a Kubernetes object is just a Kubernetes manifest. The last thing you need to do is we need to install a storage class and the volume snapshot class. These are Kubernetes native objects, pretty much linking the Trident driver to a Kubernetes storage class that can then be used for requesting storage. And this is also a Kubernetes manifest. Now, the cool thing here is what you can see on the right-hand side. All of these necessary configuration steps are done as code and can be automated quite straightforward. For example, by using Terraform, Argo CD, something like that. This is also one of our big learnings. Now, if you have a look at the configuration, or the backend configuration of NetApp, then this will look something like this. You will have an object, as I mentioned before, called Trident backend config, which will take all your NetApp, more or less NetApp specific configuration parameters that will definitely be familiar to your storage administrator. Things like the management interface, the data interface, the storage virtual machine, the usage of CHAP for authentication. So all of that. And there is also a link to a secret containing the credentials, which is actually a very, from a Kubernetes security point of view speaking, a very good way of coping with credentials, but also need to add a comment to that later. So you're pretty much having all your credentials here in one secret, username, password, your CHAP credentials, etc. And this represents all the information Trident needs to configure one backend. So one connection to Trident, if you will. And this is pretty much it. Once you've configured that and the connection is successful, you can create storage volumes, persistent volume claims with that storage class, which can then be used in a virtual machine, either as code or in the Harvester UI. Now, the third part here is Kubernetes storage, and I'm here specifically speaking here about Kubernetes clusters that are installed on top of virtual machines. Now, the idea is pretty much the same as before, since this will also just be a Trident CSI driver installation, but it's important to mention that we're going one logical level up. So we're not running iSCSI from the hardware operating system, the SLI Micro, but from the operating system of the virtual machine, from the IP addresses of the virtual machine that is hosting this Kubernetes cluster. So in that case, the virtual machine becomes the iSCSI initiator, talking in storage terms. The schematics will look something like this. We have our hardware nodes, we have our SUSE Virtualization RK2, we have our virtual machines on top, and then we have another Kubernetes cluster, for example, RK2, installed on top of there. There we install Trident, create our pods, and want to assign a persistent volume claim, persistent volume or storage to one of these pods. Now, what will then happen is, again, we need to install and configure Trident. Then we definitely need to ensure that this virtual machine has access to the iSCSI target, which is the data interface of NetApp. So you need to make sure that the VM IP is able to connect to NetApp. Just make sure that the IP addresses, routers, VLANs, etc. Are properly configured. You then need to make sure that also multipath tools are installed and configured correctly on the virtual machine. Same is true as for the configuration we had before, where we actually took care of the multipath configuration as a custom resource definition. This might not be possible here anymore, but you can just use Cloud Init, a Cloud Init script of part of the virtual machine definition. So this is something that comes out of the box with SUSE Virtualization. Initialization of virtual machines via user-provided cloud init scripts provided as the configuration dialog in SUSE Virtualization. So you can also use cloud init again, which keeps the tool stack quite neat, which is nice. The workflow is then pretty much the same. The Trident, just the Trident in the child cluster, will request and create volumes on NetApp, and then actually the data flow will go, of course, through the hardware, but then it will go through the IP address of the VM, mount the target or mount the volume in the VM, and make it available as a Kubernetes storage object to the pod. All right, now which lessons did we learn? Well, one of the lessons we learned is that if you install the Trident operator and all its configuration in the same namespace, and you just want to get rid of the namespace at all, you will run into problems with the finalizers, which is perfectly fine. Kubernetes design-wise perfectly fine, but still we had some problems there. So the solution here is to just look for all the objects that have finalizers, delete them first, then you might want to delete the operator, and then you can delete the namespace. Just take care of your order. This is nothing extremely sophisticated, but is something that can get tedious, especially if you just want to get rid of the namespace and expect it to delete everything inside it. This will not happen. This will not work. So you need to mind your order. What we also learned is that the troubleshooting capabilities of Trident are actually really nice. So if you want to troubleshoot Trident, for example, you're missing a firewall rule to access your NetApp by a virtual machine, for example, and you're just being blocked by network side, the status of the configuration items in Kubernetes and also the output of the operator is very good. So you will definitely find an error cause within seconds there. You just know where to look. And if you know that Trident works with custom resource definitions and you know which ones to look for, namely the backend configuration template, and the operator, you will find a problem very fast. But probably try to stick to a tool like K9S, because otherwise you will just do a lot of typing with kubectl. Trust me, you'll use it a lot, especially in your first installation. Now, the configuration feature of Harvester via cloud in custom resources, it's great. It's absolutely great. You can pretty much customize your whole operating system without having to log into or having to SSH into the nodes at all, which is amazing. And the cool thing here is you can have everything as code. For one project that we did, we had the whole configuration from scratch as Terraform, from machine deployment to the cluster provisioning and to application deployment. And you're just very fast when it comes to disaster recovery, to reproducibility, transparency, etc. So the more you can do as code, the better. And with Harvester, you can do pretty much everything as code. And what we also learned is that the NetApp Trident docs, at least the rendered official ones, are somewhat confusing, to be honest. The silver lining here is that the GitHub repository that's apparently behind that, NetApp Trident docs, NetApp docs/Trident, is actually very good. So the markdowns there are, from my point of view, better organized, and we could find everything we needed there within minutes, which is actually quite nice. So maybe just go to the source of the documentation, the source of truth, and consume your documentation from the GitHub repo rather than the rendered ones online. All right, as I said, our number one lessons learned, which is perfectly capable with SUSE Virtualization, do everything as code. SUSE Virtualization has a great API. There are more and more things going to be implemented via the API. And since it's all Kubernetes based, you can also just use Kubernetes manifest for many things. You can use HashiCorp Terraform. You can use Argo CD for deployment purposes, for managing purposes. So you have all of your CI/CD and GitOps tools available in that context. Make use of them, make heavy use of pipelines, automate everything, and everything as code. Now, I'm going to leave you with a little outlook and some things that are good to know. First and foremost, I want to highlight that the SUSE Virtualization roadmap is actually publicly available at their GitHub repository, which is a great source of information. So definitely have a look into that. You can also see, for example, the progress of their currently anticipated milestones there, open issues. So this is actively maintained and gives you a good feeling of where the project stands and where it's going. The second thing I want to highlight here is that SUSE launched a certified storage for virtualization programs for storage vendors. This was communicated in the SUSE blog on December 2nd. So I'm very much looking forward also for storage providers like NetApp to participate in this program, this partnership, and to even more improve their integration into SUSE virtualization, technique and documentation wise. Another great source of information is the Harvester knowledge base. You will also find some great articles regarding networking and storage there. Just be aware that it's a somewhat different URL. So if you have a look at harvesterhci.io/kb, like knowledge base, you will definitely find some valuable insights there as well. And I'm going to leave you with the new and upcoming release versions. Harvester 1.4.2 is anticipated to be released in February. So maybe by the time of you seeing this, it's already released. Will definitely be the case before the next major release, 1.5.0, which is anticipated to being released in March. And this is also the release, assumingly providing the VM root disks, external storage support. So very much looking forward to that one. Well, I'll leave you with a big thank you, and I would love to see you on site on SUSECon. Goodbye, I'm Daniel.